Swayam Prabha. Digital India. Educated India.
You know what does this term mean? Identical and independent distribution. Why distribution? See this bunch of n random variables, I say they are IID random variables. You are correct in the sense that so IID stands for that these random variables come from the same distribution and they are independent as well. So, say for example, you have a normal distribution and you draw n random variables out of it and then do something with it, right. Okay. Now, what I do is I look at this bunch of IID random variables and I define a new random variable as follows. So, quickly figure out what is expectation of x. So, NEX EX say 1, right. What about variance of x? Do. It does not help, pain on your heads. Huh? EX. No, tell me variance of x in terms of the variances of this x1 to xn. See, x1 to xn are IIDs. So, that means their variances are also same, right. Okay, fine. So, now what should be variance of x? Come from the basic definition, they are independent. So, variance of summation of xi should be summation of variances of, but there is an n there, remember that. Yeah. So, what is your final answer? There are n terms in the numerator, right. You are looking at variance of this. So, what would happen? N would come outside as 1 by n would come outside as 1 by n square. right? Everyone knows this, right? By variance of summation of xi's, they are independent. So, individual variances add up. So, this is n of variance of x1 by n square. So, this is variance of x1 by n, right. Now, this tells you a very interesting story. Say for example, I have a randomized algorithm for any one of the jobs in streaming algorithm, where you have found out an estimator. Say you have found out an estimator, that is one of these x1s. You run the algorithm again. You run the algorithm again, right, n times, and then look at the new random variable as this one. So, n runs of your algorithm, right. See, in streaming the constant is space. So, as the stream comes, I can do parallel computations, right, at the expense of some more space, fine, but I can do parallel computations. On the same stream, I can do parallel computations, right, and I compute this x1, x2, xn, n different estimators of the same thing. Then say as the final answer I return the summation of xi by n. What happens is, whatever the expectation was remains same, but the variance goes down, and if the variance goes down, your knowledge on Chebyshev tells you that, so Chebyshev had a variance term in the numerator, so that probability would go down. So, this is an application which I will use later on. This is a very classic use in, it has its very classic use in algorithms, whereby I take independent copies of the same thing and add. Some more basics before I get into, because I would use them. There is something called conditional expectation. So, how do I define it? So, the summation is over all small y values that the random variable capital Y can take, right. So, the convention is, when I write these alphabets in capital letters, it means the random variable, and small letter means one of the particular values that this random variable is going to take, fine. So, this is the definition of conditional expectation. So, this summation is over the entire domain of values that random variable capital Y is going to take. small caveat, as in the earlier case, the summation is over all possible values of y and the expectations should exist. Okay. So, think of this as a kind of a weighting scheme. What I am doing is look at this random variable x, capital X, right. I am conditioning it on different values that y can take and multiplying it with kind of its weight, which is nothing but the probability of capital Y taking the value small y, right. So, one can prove this result. So, let me even write a small proof for this. Get into the definition of expectation. Sorry. Right. So, this expectation is this one. These are kind of two sums and you are taking product. So, you can write it as double sum as well. This is nothing but the chain rule that we did, right. We did a application of this in the morning. So, this is probability of x equals to x intersection y equals to y. Now, look into this quantity. So, if you kind of fix values of x and then look at those quantities, you are looking at all possible intersections that y can have with x, kind of summing it over. That is nothing but probability of capital X taking the value small x. And this is by definition expectation of x. Right. So, remember this, I mean, even if you do not remember this proof, this is one thing that I will use today when I get into a streaming algorithm. And this is a, I mean, when you are in difficulty computing expectations, this way becomes easier. So, what you do is get hold of events that on which you can kind of condition x and look at all such conditionings, sum over. So, one can even show that this linearity of expectations, I will not get into the proof of it, maybe to put it in the tutorial. So, you can kind of have a similar linearity of expectations in this regime of conditional expectations. So, if you want it as a formal statement, for n finite, these are say n discrete random variables with finite expectations. The same thing, linearity of expectation holds in case of conditional expectations as well. Maybe you can do a corollary exercise of it. So, expectation of, if I write this, what should this be equal to? Hunch? Huh? Good, very good. Prove it. So, prove this as an exercise. এইটা একটু ঢুকিয়ে দিও। Anyway, so this is kind of, let us now get into streaming algorithms. Too much of mathematics. It's kind of your third streaming algorithm. Approximate counting. So, the setting is as it was in the morning, a router and network traffic passing. Say I simply want to count how many packets went past. What do I do? Have a counter. Say for example, I like you are sitting in Coimbatore and there is a hub in here and packets are getting routed to Mumbai, Hyderabad, Kolkata, Delhi, Chennai, so on. And I just want to figure out how many packets did go to Hyderabad, right. So, the moment I see an IP address there, I increase the count by 1 in a counter. Done. So, how much space would it require? Log n. Can I do better? Can I do better? Better than log n? Hmm? What? Log n is easy to see, right? Can I do better than log n? Okay, let that space be Fn, some Fn, right? So, then 2 to the power of Fn is what you can represent, right? You are dealing with binary bits 0 1, and if you are now you say that Fn is the number of bits, then you can look at 2 to the power of Fn is the possible number of configurations that you can handle. That should obviously be greater than or equal to n. What are you counting? So, this implies Fn should be greater than log n. So, that this tells me that if I am counting exactly, I cannot possibly do better than log n. Now, what if I am allowed to estimate? I will be happy with an approximate answer. Maybe what? See, now you are allowed to err, so you can make an error. Go ahead.
Maybe we try patching, like first K as one, patch it approximately, there are more or less errors.
Did you get what she say? What she is saying? Think of this. Things are coming, right? So, I count first 1, 2. So, this is like 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, so on. Say for example, if I can think of storing these things. So, say for example, I can store these 3 and 4, right. Then I know that my value is somewhere in between. So, I would kind of make it 2 to the power and I will say, so that means for any value in between 8 and 16, I will say it is 16. An idea like this might work, right. So, the moment I you are making big jumps, right. This is an exponential function 2 to the n, it is kind of 2 to the I. So, if I can kind of focus on the indices and store the indices, so then how much space would kind of I can with how much space can I manage this approximate answer? N is what you have to count up to, right?
A is the maximum space.
Right, but now I am not exactly counting n.
Yes. So base log n log.
Good. What is this? What is this? Right? So, I need to store at most this. So, log of n, that is the rough idea. I will err, I will bring in probability obviously, because I want an epsilon delta kind of an algorithm that I talked of in the morning, but this is the basic idea. So, did you get the idea? Any queries till now? Okay. So, let us now get in.
So here we are
I have not given you the exact algorithm as yet. What I am trying to do is I am trying to make you feel how possibly an algorithm might work. Yeah.
so here we are concerned about space or time or
Space, we are in the streaming world. Yes, we are concerned about space. Time we are not much bothered about. This was kind of one of the first, you understand that how basic is this job, right? Just counting. So, this algorithm comes from someone called Morris, and this is kind of one of the first algorithm to for in streaming. Okay, maybe I can just write out what. So, our goal is to design a streaming algorithm that counts a sequence of particular events. So, and when you query, it outputs an estimate, right. So, think of this model, this router model again, packets going by, I keep counting, I put a some value in the counter, and whenever you ask that how many packets to Hyderabad has gone by, I will give you an answer, right. Okay. Let us see how we bring in probability. So, there are 3 steps: initialization, because later on I will kind of do an induction. So, I need to fix the base case. Now, this sets x to 0. In your update step, here is the crucial probabilistic argument. when you are queried, you output an estimate equals to 2 to the power of x. This minus 1 is a correction term. Why it is there, we will understand a little later. Now see, what I do? I increment x with the probability of 2 to the power of minus x. Why do I do it? 2 to the power of minus x. You are waiting for success bound, which Uddalov did for you yesterday in this coin tossing thing. For a probability of p, I know that on the expectation you are supposed to get a success after 1 by p, right? Does this simulate this one? On the expectation you would be adding 1 for this range, right? Whatever your value is currently, you increment that, make x equals to x plus 1 with a probability of 2 to the power of minus x. So, 1 by 2 to the x. So, that means in expectation for a range of 2 to the x, you increase it by 1. So, this idea I handled probabilistically in this fashion. Have you got this one? If you have got this one, the rest is like maths. We will do an analysis. If you have difficulties in understanding this, let me know. So, this is an estimate, remember. We will later on show that this is an unbiased estimator. That means, if you take expectation of this, it would turn out to be the quantity that you are wanting to count. Mind you, this n hat is a random variable, right? Why? Because I have done this. X is now a random variable, and we have already argued that the function of a random variable is also a random variable. So, this estimate that you are throwing out is a random variable. Okay, so your intuition is that I mentioned